All right, everybody, let's talk thermodynamics. Thermodynamics is driven by the atomic behavior of all the atoms inside of an object. All right, so first off, remember from gases that we found out that atoms are in random motion. This motion is spread out over kinetic energy or speed distribution like we have up here. So a cold object, most of its atoms will be down here with a small kinetic energy, and hot objects will be spread out farther with higher kinetic energy objects. There is an average kinetic energy, remember, that we have this peak, and so we kind of have sort of a bell-shaped curve, so we have kind of an average, and that the temperature of an object tells us what this average kinetic energy is of the atoms inside of an object. Heat transfer. Objects that have a different temperature will transfer heat. So I have a cold object down here. Notice all the atom speeds are crunched down here in the lower speed area, and a hot object, the atoms are spread out farther this way. Now, due to this random behavior, we end up with more atoms moving faster in the hot object than in the cold object. So when we put these in thermal contact, heat will naturally transfer from hot object to cold object. Actually, what we end up is heat transfers between hot to cold and cold to hot, but there's much more likely that hot atoms moving faster will collide with slower moving cold atoms just because statistically there's more of them. So we end up with more heat transferring through these atomic collisions from the hot atoms to the cold atoms, even though there are some from the cold to the hot. So the net effect is always that heat flows from hot to cold. Always, always. Since this net effect is going from hot to cold, what we end up with is these atoms slow down, these atoms speed up, and so they reach this equilibrium distribution. If they have the exact same number of atoms, the curves will completely lay on top of each other perfectly. If, on the other hand, that we have more atoms in one than the other, the curves will have the same shape. One will just be taller than the other. Heat flows from hot to cold until they're both the same temperature. Now, when they're the same temperature, heat's flowing back and forth at equal rates, so the net effect is that there's no heat transfer anymore. All right, there are three mechanisms for heat transfer. There's conduction, convection, and radiation. So if you stick something in a fire, it gets hot, the atoms down here collide, and the ones down here are moving faster, and they collide and heat up the colder ones up here. If you put your hands above the fire, you'll notice that you feel the hot air rising. This is convection. And if you put your hands to the side, you'll feel the radiation just from the atomic spectrum, E&M spectrum, radiation coming off the object. Now let's talk about conduction first. Heat transfer occurs due to the atomic collisions from one atom to the next, all the way along the length of the object. The rate that heat transfers, that's delta Q, heat, over time, is proportional to the area of contact and the temperature between the two ends of the object, and it's inversely proportional to the length. Okay, so like here's a pathway here. So I have this brick here that it's hot on one side, it's cold on the other. So the higher the temperature difference, the faster heat will want to try and push through. The longer the path, the slower it'll move through because it just has a longer path. And the bigger the contact area between the hot side and the cold side, the more likely heat will pass through. So we end up with this equation right here, delta Q over T, which is the heat transfer rate, is proportional to the temperature difference and the area of contact. And then this K, which has to do with the thermal conductivity of the material. So metals have a high thermal conductivity. So since they have a high thermal conductivity, heat will transfer faster through them. Things like cotton and porcelain and things that we use for insulators, like the stuff we put in our jackets and coats, they will have a low thermal conductivity, and so the heat transfer rate will be less. The thicker we make our coat, or a blanket, or the insulation of a house, the slower the thermal conductivity will be as well. If I have a hot block over here and like an ice water bath over here, and I connect them with a metal rod of length L, And I put a little temperature sensor on here. What's going to happen is the heat transfer rate is going to be great at first because we have a temperature difference of 100. The length of the rod's not changing, the area of contact's not changing, the material's not changing, but the temperature difference will become less and less and less as time goes by. So this will cool off to 90, that'll cool up, heat up to 10, and so forth. So what happens is we have a really quick change in temperature at first, and then it has an exponential change until we get to the final equilibrium temperature. So the equilibrium temperature between these two looks like it's going to be 20 degrees. Objects made of different materials will transfer heat at different rates. So here I have a problem for you. I have two metal rods that they're same dimensions and they're connected end to end as shown in the figure. The left and right ends of the rods are connected to a 40 degrees Celsius and a 0 degrees Celsius temperatures on the ends. And the rods are allowed to reach a equilibrium temperature as these 40 and 10 degrees are held constant. Temperature along the rod is measured and shown in the figure. So you can see here, this must be where the hot end is. It's 40 degrees. This must be the cold end over here at 30 centimeters. It's 0 degrees. And we have a change in temperature along the nickel rod and a change in temperature along this unknown material. And so the question is does the unknown material have a larger or a smaller thermal conductivity compared to nickel? So what do you think? Well, it's maybe a little counterintuitive, but if you think about it, the area of contact is not changing, the length is not changing. If you just look at the two things that we have that are changing, that are different, is the thermal conductivity and the temperature difference. We have a temperature difference in the nickel of 30 degrees from end to end. And the temperature difference of the unknown metal is only 10 degrees from end to end. And if you move the K to the other side of the equation, we can see that the change in temperature is proportional to 1 over K. So the unknown material, which has a smaller change in temperature, must have a larger thermal conductivity than nickel. So think about it this way. Imagine what the graphs would look like if the thermal conductivity was 0. If there was no heat transfer between the ends of the object, then say like if this nickel had a thermal conductivity of 0, that means no heat would transfer through. So one end would be 40 and the other end would be 0, and there would be no heat transfer. The temperature difference between the ends would remain constant. However, if we had a thermal conductivity of infinity, that means that heat would transfer through the material infinitely fast, and so both ends of the material would reach the same temperature nearly instantaneously, and so we would have both ends being the same. So like imagine that this had an infinite thermal conductivity. So what we'd end up with is it would be the same 0 and 0 on both ends. So the higher the thermal conductivity, the lower the slope on this particular graph, or the lower the temperature difference between the ends. All right, let's talk about convection. When a hot object is in contact with a fluid, it heats up the fluid, and when the fluid heats up, its temperature gets higher. When its temperature gets higher, remember PV equals nRT, the volume is proportional to the temperature. So as the temperature goes up, as heat flows into the fluid, the volume of the fluid goes up. Now, the fluid is now less dense than it was before because it has the same mass as it was, but the volume has gone up, so its density has gone down. And since the fluid now is less dense, it receives an upward buoyancy force that's now greater than what its weight is. It's less dense than the air around it or the fluid around it, so it gets pushed upward and flows up. So hot fluids rise and cold fluids will sink. One thing to remember about convection is that this only happens in a fluid because the fluid can change density. Now let's talk about radiation. All atoms in the object are in constant random motion. Remember that everything's made up of atoms and they're always moving randomly. But these atoms are made up of protons and electrons, which are charged particles. And remember that a moving charged particle will generate an electromagnetic wave, particularly if it's oscillating. Thus, all objects that have a temperature, meaning they're vibrating, are always radiating electromagnetic radiation. You actually, because of your temperature, you're radiating in the infrared spectrum. Now, objects that expel more radiation than they receive will cool off. So this is why you warm up when you're in the sun. You're receiving more radiation than you're emitting. So out in the sun, the temperature of the sun is much greater than the temperature of you, so it's emitting more radiation than you are, and so you warm up because of the radiation difference. Entropy is a measure of the disorder of a system. Remember, the atoms are in random motion, and so they're statistically unlikely to all move in the same direction at the same time or move in some orderly fashion. They're much more likely to move in some disorganized random fashion. So here's an example over here. If we have a one atom system and say the atom can either move to the right or to the left, we have two possibilities for what can happen, right or left. So that means we have a 1/2 of a chance or 50% chance of getting the atom to do what we want it to do, say move to the right. Now what if we have a two atom system? So we have two atoms. They could both be moving to the right or both be moving to the left. One could move to the left and right, or the other way around, move to the right and then to the left. So we have four possibilities, 2 to the second power of possibilities and what the atoms could do. That means if we both want them to move to the right, we have a 1/4 chance of that happening. Now, think of an object, a real object like a baseball. A baseball is made up of approximately 10 moles of baseball atoms. So that is 2.06 times 10 to the 24th atoms total. Now, if all the atoms can either move just to the right or to the left, 2 to this power, 6.02 times 10 to the 24th, that gives us an insanely unimaginable number, which means that it is statistically unlikely that all the atoms together will move to the right at the same time, and the baseball will move in an orderly, organized fashion. It's just not statistically possible. So whenever something is done in a random fashion, we tend to get a disorganized result. It's highly unlikely that somebody just throwing bricks in the air, that they're going to land all like this. What's more likely is they're going to land in some crazy pile. Or if we have atoms, say cold ones and hot ones, in a container, it's much more likely that they'll spontaneously mix together than they'll spontaneously separate. More disorganized means more entropy, and things move naturally to more entropy just because it's more likely for it to happen that way. The change in entropy is given by this number right here, delta S, and it's measured by figuring out if heat is going in or out divided by the temperature of the object. Two identical rooms are separated by a door. Each room is filled with identical air, except that one room is hot and the other is cold. When the door is opened, is the change in entropy positive, negative, or zero for the hot air, cold air, and for the system that includes them both? So when you open the door, they mix, they end up as warm air because we know heat flows from hot to cold. So what will be the change in entropy of the hot air, the cold air, and the grouping, the system of both? Heat flows out of the hot air, so its entropy goes down. Heat flows into the cold air, so its entropy goes up. But the entropy of the system as a whole will also increase. And that's because the temperature of the hot air was larger than the temperature of the cold air. So the rise in entropy of the cold air will be larger than the decrease in entropy of the hot air. So we end up overall with an increase in entropy for the combined system. This means it's an irreversible process. and it can't be naturally reversed. It won't naturally go the other way. Things always move towards higher entropy naturally. Anytime heat flows between objects, the entropy will increase for the system of interacting objects. Heat flow is natural, and it's also irreversible. That means there's only one way that heat flows, from hot to cold. And if we want to reduce the entropy of the system, it won't happen naturally. We would have to do work on the system. That's why every summer down here in the hot, hot state of Texas, that we have to have our air conditioners running to do work to separate that heat back out of our house, because it naturally wants to flow in. It won't naturally move outward. Entropy gives us what we call our sense of time, because entropy always increases, which means that we can always set things up or understand, like say a series of pictures or events that happen by just looking at their entropy level. The ones that are the oldest, are the farthest back in time, will have the lowest entropy. The ones that have are the most recent will be the ones that have the highest entropy, because we can always set the pictures up or the events up in increasing entropy order, and that's the same as the time order. And that's it. Our next video, we will talk about the first and second laws of thermodynamics in more detail. Until then, bye-bye.